speaker of the morning. We have Gabriela Planas, and she's going to speak to us on non-homogeneous Navier-Stokes system with Navier friction boundary conditions.
Thank you. First of all, I would like to thank the organizer for the invitation. I am glad to participate in one more edition of the workshop on Fluids and PDE. I'm going to talk about this problem, an homogeneous Navier-Stokes system with Navier boundary conditions. This work is in collaboration with Lucas Ferreira and Elder Villamizar Roa. The outline of my talk is, at first, I will introduce the system. The Navier boundary conditions was mentioned in some talks this week. After that, I will discuss the existing solutions, and finally talk about the inviscid limit for this system. Okay, the system we are interested in is the non-homogeneous incompressible Navier-Stokes equation. We have the momentum equation. U is the velocity, rho is the density of the fluid, pi is the pressure. We have the divergent free condition for the velocity, the continuity equation for the density. All the equations are valid in Q, which is the cylinder omega times the interval 0 t. Omega is a bounded domain in R3 with a small boundary. And here we have the parameter nu is positive, is the viscosity coefficient of the fluid, and F is an external force. We supplement this system with boundary condition and initial condition. We will consider the Navier boundary conditions. There are these two conditions. The first one says that the boundary is impermeable. The second one is a condition over the tangential component of the velocity, which is proportional to the deformation tensor. D of U is the deformation tensor. In fact, it's the symmetric part of the gradient, and it's a stereo normal to the boundary. And here we have the coefficient alpha, which is non-negative, which measure the tendency of the fluid slip on the boundary. This is the meaning of the constant. We have also initial conditions for the density, which could be 0. Yes, it's greater or equal to 0. And another condition for the momentum is initial momentum, which is a product of the density and the fluid velocity. To be consistent, we ask for the momentum to be 0 whenever rho 0 is 0. Okay, let's make some commentaries about the Navier boundary conditions. Navier was the first to examine the possibility that the fluid might slip at the solid surface. This was in the original paper Navier in 1827. Also note the Navier boundary condition was derived in the kinematic theory of gases back to Maxwell in 1879. Recently, the experiments have demonstrated that the phenomenon of the slip actually occurs, especially in the microfluids at the microscopic level. This is a paper of Neto and a lot more people. It's a review of many experiments which show this kind of phenomenon really occur. It's happened. From the mathematical point of view, I can see Jagger and Michelet in 2001 rigorously justified the Navier boundary condition as a homogenization of the knots Elite condition on the rough boundary. It's kind of motivation for them to use the Navier boundary condition. Okay. Let's talk about a little bit about the existence of solutions. There are some existing results. We can divide the existing result with Dirichlet boundary conditions that are more usual in two types. One is when the initial density is assumed to be positive, and so there is no vacuum initially. Okay, there are results. One is this kind of the results assuming this condition, and the other one is assuming that the initial density could be 0. Okay? There are results concerning the global weak solutions, one of them, and local strong solutions, also in Hilbert space, Sobolev space, and so on. But see, all these results are related to Dirichlet boundary condition. Also talking about Dirichlet boundary conditions, see, we turn to the case with the initial density could be 0. Then there are fewer results because the problem is more difficult to handle. There are some results of existing of solution, some work of Simon, Kim, or the books of Leon. And related to local strong solution, more recently there are the paper of Choi and Kim in 2003. What about another kind of boundary condition for this problem? Only one is, well, I know of Ito in 2000, who proved the existence of strong solutions. It's not exactly a Navier boundary condition, it's a general sleep boundary condition. But he assumed that the initial density is greater than a constant positive. No vacuum zones are admitted. So our first goal was to prove existence of solution to the non-homogeneous Navier-Stokes equations with Navier boundary condition and allowing vacuum, assuming the density could be 0, rough condition, the external force in initial data. Let's make some comments. Well, okay. First, I'm going to introduce our hypothesis, our assumption on the data. We will, ρ0 will be in LP, P between 6 and infinity, could be infinity, can be 0. The initial momentum is Lebesgue space. We satisfy this B0 squared over ρ0 in L1. Okay, this is the external force belong to space L1 in this Q to P over P minus 1. Okay, what is the mean of B0? B0 formally corresponds to the initial value for rho times U. And this is ρ0 squared over ρ0 is the initial value for the product rho U squared. Formally, is what's the meaning of these functions. When P is equal to infinity, this is LR exponent dependent of P should be understood in the natural way. That is, as the limit when P goes to infinity. This is become L2, this become L2. Okay, let's introduce the way we understand our problem, which is the definition of the weak solution for our problem. Okay, it's a pair of functions, u, rho, satisfying this regularity. This is the velocity is L2 with values in H1 and sigma is divergent free. Okay, the natural space for the density could be 0. So we don't have information, for instance, as usual in L infinity L2 for the fluid velocity. We have information about the product, this product, because we don't have a bound from below for the density. So we have all information about this product, rho times u, root square of rho times u, and rho u. The information about the regularity. Okay, this function satisfies the equation in this sense. The continuity equation in the distribution sense. This is a quick formulation of the momentum equation. Here we have only integrated in time by parts. Here, these two terms came from the Laplacian. In fact, I will show the integrate by part, the formula of integrate by part in this case it is one. The Laplacian times g, using the d of f is symmetric. I use it is divergent free. We integrate by part, we have this boundary term, and we use Navier boundary condition to replace this term with the information of u. This is, I will back at the formulation, this is the reason appear this boundary condition here with the alpha coefficient in that place. Okay, the other terms are usual. It's a nonlinear term, the external force, and the information about the initial momentum here. Moreover, the weak solution that we construct satisfies the energy inequality. This one. Formally, we take the test function u. In fact, we use an approximation problem that we have the energy inequality for the approximating function and pass through the limit. But I would like to remark here, we have information, as I say, we don't have a bound from below for the velocity, for the density. So we have information about the regularity of this product. Okay, about the boundary of the symmetric part of the gradient. But the regularity of u is in H1. You need to use some kind of cone inequality to obtain information about the gradient from the symmetric part of the gradient. However, the cone inequality needs the norm L2 of the function. But there is another cone inequality, it's more general. It's in this book, it's of Fares and Nobody, new book, 2009, where they have this cone inequality to relate the symmetric part of the gradient, a product here, which in our case R will be rho. Yes. Then with this bond, in this bond you have information, you have a bond in H1. So this part and this part give the regularity in H1. Okay. Our theorem say about existence of weak solution is there is one, at least, with, in the sense of the previous definition. Of course, if rho 0 is strictly positive, then the weak solution will satisfy L infinity in L2 as the usual. The proof is easy. Okay, let's comment compare this our approach with the previous ones, the Leons and Kim, for Dirichlet boundary conditions, and when they also allow the initial density could be 0. Leons employ an approximation based on the characteristic method and a linearization of the momentum equation. The initial density in L infinity, the initial momentum in L2, F is a little more regular, and the viscosity, continuous viscosity depending on the density. Kim use a semi-Galerkin approach, combining with the characteristic, also with the characteristic method. Consider initial data in L infinity, a more regular initial velocity and external force. Our approach is different. We perform a combination of strategies of Simon. Simon also considered rho 0 in L infinity, but less regularity on the data. But use some ideas of Fidels and of the book of Fidels of 2004 is a book of compressible fluids. Together with some ideas coming from parabolic PDE. I will be more precise about our approach. We first introduce a regularized problem, depending on small parameter epsilon, will be positive, which is constructed by a regularization of the continuity and momentum equation, as well as regularization of the data. Okay, I will show the system, the regularized system. Okay, we have the momentum equation. The first, all the terms are the same. We have an additional term here, depending on epsilon. When epsilon go to 0, this will disappear. We have the divergency precondition. We have a parabolic regularization of the continuity equation. We add the epsilon Laplacian or rho epsilon. So we need an additional condition, boundary condition to complement the parabolic equation. This is a Neumann boundary condition for the density. We keep the Navier boundary conditions for the velocity. The initial data depend also on the, as I say, depend on the epsilon. It's a suitable regularized functions. In fact, rho 0 epsilon is moved, of course, satisfies the Neumann boundary condition. One of the important thing, the approximation is strictly positive. Okay, the measure of this set go to 0 as epsilon go to 0. And we have, of course, convergence in LP, strong and weakly starting in L infinity. And the initial momentum also is regularized in this way. B0 is when rho 0 epsilon is greater or equal to rho 0, and 0 in another case. When this epsilon goes to 0, this set, the measure, go to 0. So in fact, rho 0 epsilon converges to B0. We have used a parabolic regularization of the continuity equation. We consider also initial density in LP, was not considered before. And the techniques are different of the other ones. How to solve this? The idea is to solve this regularized problem is send epsilon to 0. Okay? Then it's natural. This term will disappear, and this term will disappear. We will expect to obtain our problem at the limit. To solve this problem, we use Galerkin approximation. In fact, we obtain weak strong solution to the regularized problem by Galerkin approximations. We use some result of parabolic equations to resolve the regularized continuity equation, show the fixed points, a priori estimate, and compact argument. But in fact, we have one regularized problem and one approximated problem. And finally, to pass to the limit, well, we pass to the limit in the approximated problem, and we pass to the limit in the regularized problem. We need some estimates. There are some kind of technical points. I'm going to show this estimate. I only would like to give the idea. I hope to prove the theorem. Okay, let's show how to construct the approximation problem in the fixed point operator. We take a basis of H1. We take an approximating function f, converting to fm, converting to f. Here, in fact, is exactly the parabolic problem. Here we use Galerkin. Yes, this is the Galerkin. In fact, it's a system of the idea is to do that. Given UM, solve this problem. This is a parabolic problem. You have a system uniqueness of solution. Given the solution of this problem, we put here. And given the same U was UM, we linearize this system. Then we have a linear system of OD, because rho will be given in this problem. Then we have a point, a fixed define an operator, which fixed point is the solution. Then we perform estimated independent of epsilon, and the independent of m, and independent of epsilon, and pass to the limiter first in m and later in epsilon. It is more or less standard. Okay, let's do the second part of the talk, which is the inviscid limit. Formally, see, when we drop the viscous term, that is taking the viscosity equal to 0, the non-homogeneous incompressible Navier-Stokes equation transforms in the non-homogeneous incompressible Euler equation. Yes, the difference with the original problem, we don't have the Laplacian here. This because the viscosity is 0. The divergence free condition, the continuity equation. We keep only one condition for the velocity, this tangent to the boundary. Okay, the initial density, the initial momentum. We would like to justify this formal procedure. Okay. This problem, since we consider the wall space or with periodic boundary conditions, it was already proved by Ito, Tarid, and Shan. Okay, they assume the initial density is positive. And they prove convergence of local strong solution in Hilbert, and some of them in Hilbert, or another one in Sobolev space. So if we consider now the bounded domain, we expect the same problem with the homogeneous case. It could be happen the boundary layer phenomenon. So we put not a sleep boundary condition. Well, many people talk about this week. And these people talk, okay, the Navier boundary condition works well. It's true. So we supplement the problem with, in the homogeneous case, with Navier boundary conditions, it's possible to prove the convergence of solution, the Navier-Stokes equation to the solution to the Euler equation. Okay, there are many works about this subject. These are only one of them. So our idea is to do some similar or extend this result to our problem, to the non-homogeneous incompressible Navier-Stokes problem and prove the convergence this solution to the non-homogeneous Euler equation. So it is the second to prove this convergence. We are in dimension 3, so our idea is to show the solution we construct, the weak solution, which satisfies the energy inequality, converge to the strong solution to the Euler equation. Why we are going to consider a strong solution of the Euler equation? Because there exists. We know there exists. Then the idea is to prove we converge from something that exists. Well, the idea, in fact, is analogous to the case of the homogeneous case. Is to compare a smooth solution of the Euler and a weak solution of the Navier-Stokes equation and obtain some energy estimate and apply some using Grunwald argument. As a comment, this approach arises suitably in view of the fact that only strong solutions are known to exist for the non-homogeneous Euler equation. This is the same idea or similar idea when we prove result for weak strong uniqueness. This compared with weak solution and a strong solution. Okay, there are some reference about the existence of strong non-homogeneous solutions of the strong solution of the non-homogeneous Euler equation. We will consider with more suitable to our situation the solution given by Bali and Sadkowski. This is a little more general, I think. The result is omega is a bounded domain, P is greater than 3, and we have a smooth initial density which is bounded from below and from above. Yes, it's bounded in both sides. This is important. In fact, we need to assume the same restriction on the initial density. Okay, the initial velocity also is in W2P. There exists a local strong solution which will belong to this space, very, very regular solution. Okay, our theorem said about the inviscid limit is take the strong solution of the non-homogeneous Euler equation, take the weak solution we construct, assume that the initial density for the Navier-Stokes equation is bounded from below above below. Yeah? From below from above. We tried a lot to remove this condition, but it was not possible. In fact, in the old space, they put this condition also. And then there exists a constant which is independent of the viscosity, such that the T star is the time existence of the Euler equation. So we compare the two solutions. The difference between the Navier-Stokes solution and the Euler solution for the velocity, for the densities, is lower or equal than, here the initial data, related to the momentum, this to the related to the difference of the initial densities. Here we have the viscosity. U is the Euler. In fact, this is the minimal regularity we need in this inequality, and this is the difference of the external force, because the external force for the Euler equation is more regular than the external force for the Navier-Stokes equation. So we can conclude from this. We can conclude different things. First, we need the initial condition converge. So the regular initial, corresponding to the Navier-Stokes equation, converge to the initial data of the Euler equation. In this, when the viscosity goes to 0. In this case, if the external force also converge, then this goes to 0. The velocities and the densities converge. This is L2 in the energy space. So this is the first conclusion here. We have convergence in fact, in L infinity in time, L2 in space, for the velocities and for the densities. Moreover, we can conclude the momentum also converge, because this is a simple trick. We rewrite this in this way. This converge, this is bounded, then also we have convergence of the momentum. By interpolation, as the densities are in L infinity, we can conclude the convergence, in fact, in LP or NP greater or equal to 2. It's not for the density, it's not only in L2, we have convergence in LP for NP. The idea of the proof, as I said, is to compare the two solutions. So formally, we will consider the difference. Is omega the difference of the velocities, sigma the difference of the density, Q the difference of the pressure. And we make the difference of the equation in the suitable way. Yes, there are many possibilities. Then one of them is work well. The idea is it's formal because we have only weak solution. This should be justified. This is only to give the idea how this works. Then we have the first equation is an omega. The idea is to multiply by omega and integrate. Here we multiply by sigma and integrate, and add the two inequalities. Okay, so the first estimate is, I say, multiply the equation of the continuity equation for the sigma, integrate in spice, use Holder and Young inequalities, and we arrive at this inequality. With this, we have bound this term using Holder and Young. We will use strongly many times this kind of estimate. We can bound really the density in L infinity. Have a bound. This is important. Okay, we do some similar with the first equation. These are energy estimates. We multiply by omega, then we will disappear. Here we have to estimate this all the time. The idea is to, we arrange terms in way that we, on the right-hand side, we put the Euler solution, we have more regularity. Then you can bound it. This is the idea. So the second estimate is multiplied by omega. We have this term. This is some trick as adding arranging term of the Laplacian term. On the other side, we have many terms, but all of this, to pay attention, they have this initial data. I have put all the most regularity on the Euler solution because it's very regular. Here, the normal 2 of the omega. Here we have this Euler, then it's all bounded. Here we have omega and sigma, a normal 2. Okay, here appear the term involving the norm of Young, is the Euler, that is his feet, and here's the difference of the external force. Then you have, you can, this is, I would like to show, we try to prove some estimate involving this product, but it was not possible for the term who appeared on the other side. Then, in fact, we bump by below this because we know it's our hypothesis. Then we can have the norm of omega here and apply Gromwell, and we deduce the estimate. This is the idea. Well, finally, apply Gromwell type estimate to conclude the inequality. So, thank you very much for your attention.